Welcome back. This is the final part of a 9-part video series on completing the square. In this video, we'll apply the completing the square method to calculus problems to solve integrals. Let's get started. There are many common patterns in math. Many problems can be solved by making the problem you are given match a pattern, which will then direct you to the solution. This is a common way to solve integral problems. There are books and websites with integral patterns and their solutions. In this video, we'll discuss how to complete the square to match an integral pattern. Here's an analogy. Imagine you need to get home. You can get home without necessarily needing to know how to walk there. There might be a bus that will take you there. So the problem would be solved if you could find a way to get to the bus. So the bus is like the mathematical pattern, and completing the square is like the method you can use to find your way to the bus stop. We start with the integral of dx over x squared plus 8x plus 41. The pattern we want to use is the integral of du over u squared plus a squared, which equals 1 over a times arctangent of u over a, all plus c. We're going to complete the square to match this pattern. We isolate the denominator x squared plus 8x plus 41. The linear coefficient is 8. Half of that is 4. And so the perfect square pattern is x squared plus 8x plus 4 squared equals x plus 4 in parentheses squared. The 4 squared can be evaluated as 16, and so we need to add 16 to complete the square. We can't just add 16 because that would change the value of the denominator, but we can add 0. And we can rewrite 0 as 16 minus 16. We can then regroup the terms. The second group of terms can be combined to be 25. The first group of terms can be replaced with x plus 4 in parentheses squared, and 25 can be replaced with 5 squared. We end up with x plus 4 in parentheses squared plus 5 squared. Our integral can then be rewritten as the integral of dx over x plus 4 in parentheses squared plus 5 squared. Now let's compare this to our pattern. U equals x plus 4, and a equals 5. We write the solution from our pattern 1 over a times arctangent of u over a, all plus c. We first replace a with 5, and then u with x plus 4. We've solved our integral. We end up with 1/5 times arctangent of x plus 4 over 5, all plus c. We had this integral and used this pattern. But what if instead we had the integral of dx over x plus 4 in parentheses squared minus 5 squared? Take note of the minus sign. It makes a big difference. In that case, you would need to use the following pattern involving the natural log. If you're up for a challenge, can you see how you might have used the original pattern but with an imaginary value for a? See if you can figure it out. Here's another integral example, but from an introductory quantum mechanics problem. Griffith's Intro to Quantum Mechanics is a common book used in a quantum mechanics course for junior or senior level physics majors. This problem is about the wave function of a free particle. Although this is an interesting topic, I'm just going to focus on the integrals used in the problem and not on the physics. Griffiths gives us integral from minus infinity to positive infinity of e to the negative in parentheses ax squared plus bx dx. He tells us to complete the square and replace ax squared plus bx with y squared minus b squared over 4a. This is like our last problem, except that we're going to transform this integral to match the pattern. Integral from minus infinity to positive infinity of e to the negative u squared du, which equals the square root of pi. This is the area under an unscaled Gaussian function, also known as a bell curve. Let's complete the square and see how Griffiths gets this equation. First, let's start with in parentheses ax squared plus bx equals ax squared plus bx. We're going to leave the group terms together on the left-hand side, but not on the right. First, we see that we have a leading coefficient a, so we divide each term by the leading coefficient. A cancels on the first term on the right-hand side. The right-hand side is now in the correct form for completing the square. So we take the linear coefficient b over a, divide it by 2, square it, and add it to both sides. The right-hand side of the equation can be rewritten as a perfect square x plus b over 2a in parentheses squared. The second term on the left-hand side can be rewritten by squaring both the numerator and the denominator to get b squared over 4a squared. We get, in parentheses, ax squared plus bx over a plus b squared over 4a squared equals x plus b over 2a in parentheses squared. Our goal now is to solve for ax squared plus bx. First, we see that the expression we want is divided by a, so to get rid of this, we multiply every term by a. It cancels on the first term on the left, and 1a cancels in the second term. Next, we move b squared over 4a to the other side, and when it gets there, it becomes negative. We end up with ax squared plus bx equals a times x plus b over 2a in parentheses squared minus b squared over 4a. Griffiths makes the clever choice to define y equals square root of a times x plus b over 2a. The triple bar equal sign is a notation which means that this is a definition and not a derivation. If we square both sides, we get y squared equals a times x plus b over 2a in parentheses squared. If we go back to our equation, we can see that this term can be replaced with y squared. When we do this, we get ax squared plus bx equals y squared minus b squared over 4a, which is what Griffiths originally gave us. Let's go back to our original integral. We can use this substitution to rewrite the integral as the integral from minus infinity to positive infinity of e to the negative in parentheses y squared minus b squared over 4a dx. We can distribute the minus sign, and then we can write it as two exponentials, e to the negative y squared times e to the positive b squared over 4a. E to the b squared over 4a involves only constants, and so is a constant itself, and therefore can be moved to the front outside of the integral. We get e to the b squared over 4a times the integral of minus infinity to positive infinity of e to the negative y squared dx. We have a function of y integrated over the variable x, so we need to change the integration variable to y. We go back to the definition of y as a function of x. We find the differential dy equals the square root of a times dx. And then solving for dx, we get dx equals 1 over the square root of a times dy. We also need to change the bounds of the integral. When x equals infinity, y also equals infinity. And when x equals negative infinity, y also equals negative infinity. So the bounds don't change. We replace dx in our integral with 1 over the square root of a times dy. 1 over the square root of a is a constant and can then be moved outside the integral to the front. Inside of our integral, we are left with e to the negative y squared dy, which matches our pattern for the integral of a Gaussian if we make u equal to y. Remember Griffith's earlier definition of y? He made that definition specifically to allow us to apply this integral pattern in this step. Clever boy! According to this pattern, the integral is equal to the square root of pi. We can move the square root of pi to the front and combine the square roots. Our original integral from minus infinity to positive infinity of e to the negative in parentheses ax squared plus bx dx equals the square root of pi over a times e to the b squared over 4a. In this problem, this is the new pattern used to solve the integrals for the wave functions phi of k and psi of x and t. To apply these patterns, you first identify the replacement for a, and then the replacements for b. As you can see, sometimes these replacements can be a bit messy, but sometimes that's how these things go. That concludes this series on completing the square. I hope you found it helpful. The purpose of this series was to treat this subject as comprehensively as possible for those who are seeking not only the ability to procedurally complete the square, but also to understand it. If you found this video and series helpful, then please like and subscribe. Let me know in the comments if you'd like more series like this one in the future. Thanks.